Swayam Prabha. Digital India. Educated India.
What we were just now talking about, we were talking about the Carnots engine, and from Carnots engine we found out that we have got a parameter after calculation of the work and Q for each of the steps, and then summed it over for the cycle. Carnot cycle is a reversible cycle. The engine is operated in cycles and consecutive cycles and coming back to its original form. So it's a cyclic process and a reversible cyclic process. And in this, we found out the key a Q and the W at each steps, and we found out the total W which is supposed to be obtained is nothing but the total amount of heat which is absorbed by the system minus the total amount of heat which is rejected by the total input of the heat which is supplied. And in doing that, we had come to, I have some problem with the PPT. The value here I have written plus, it actually should be minus. Here it should be minus. So the signs which is shown here is slightly, there is, I was seeing I have a mistake in the efficiency expressions also. So these do happen when I'm doing the PPTs, and typo errors will be there, but I will eventually correct them and upload when I'm giving you the notes. So what we had taken, for the entire cycle, the delta U was supposed to be 0, summed over all the steps, since it's a cyclic process and it's a reversible cyclic process. So the delta U is equal to 0. And in the process, what should it be? The work which should be obtained is nothing but the total amount of work which is obtained minus the total amount work which is Q which is rejected. So if I put it here, and if I can write it QC plus, I have to remember that this should be a negative sign because it's a dissipation, and then I can get to this. Okay, if I keep the plus sign, it's the total amount of heat absorbed plus the total amount of heat rejected. Total amount of heat rejected is actually minus, so we can always get back to the minus sign. So even if I write plus, and if you understand it is actually minus, then it is okay. But if it is, if I write plus, then you have ambiguity. So I will correct that make it plus. So the amount of heat which is absorbed is equal to the work done, amount of heat which is obtained, that is amount of which is he absorbed minus the amount of heat which is rejected, that corresponds to the work done. And that work, if I want to find out what is going to be that work, it will give me the efficiency of 1 minus W by QH, and W is nothing but QH minus QC, and so that is why we are going to get 1 by, if I simplify, I get 1 by QC or QL by QH. QC and QL are the same thing. Here I have written QC and QL are the same things. Not all the time I am being able to follow the subscripts of C and L. C is cold, L is lower. Both means the same. Okay. So in the Carnot cycle, which we have seen just now, we have got a term which we say, which is a new parameter which we observe, the Q by T. Q is not a state function, but what we found that Q and by T is a term which summed over all the steps will give you a value equal to 0. So if that is a condition, that is a condition for a state variable. So we have generated a new state variable which is known as Q by T, okay, which is summed over the cycle becomes equal to 0. So if I have an ideal gas, I have just now whatever I have just now derived for the expression for efficiency. Okay, I cannot change this. So the efficiency which I have got is something like this. From if I apply the QH and QW, and we can find out that by simplification that it is nothing but the ratio of the temperature of the at which the amount of heat is rejected to the surrounding, and by the temperature at which the heat is supplied to the from the reservoir to the system, the ratio of this. And as you can see, this will be always lower than the temperature at which the heat is supplied from the high temperature reservoir. So this one will be always lower than this one. So if I have this value, then the efficiency of the system will be 1 minus something, a small fraction. So it will be always less than equal to 1. It is possible to have efficiency equal to 1 if there is, if the Tc is equal to Th or the Tl is equal to Th. That means if the temperature is rejected at the it is same temperature, or there may be, say, we can say that there is no heat rejection because the temperature is maintained Th all throughout, then the system becomes uh, uh, not possible to exist. We cannot have if I have by any chance I have a system which is equal to this, becomes equal to this, then I have a efficiency equal to 0. That means the machine does not exist. We do not have a machine. So efficiency cannot be more than 1, and it cannot be 0 because Tc and Th are not equal. Th and if Tc becomes equal to Th, then it violates the law which is supposed to be given by the second law. It violates the second law that you have to have some amount of heat dissipated at a lower temperature. So what is the second law? We are going to come into the discussion in a while from now, but before that I have to discuss few parameters. So what are, when I am asking what is the isothermal absorption of heat, there are two types of heat which is there is a two type of heat transactions in the Carnot cycle. One is the isothermal absorption at temperature Th, and another one is the isothermal release at Tc. So the isothermal absorption at Th minus the isothermal release at Tc should be equal to, by the corresponding temperature, should be equal to 0. This will be a minus sign again. So this is something which I have to make correction. So that total, which these are supposed to be equal and opposite, so they are going to be, you just see, a Q is not same, QC is not same for the each of the step, neither is a T and C temperature same. Or to understand this is a path variable, this is a path variable, temperature is independent of that. So we are saying that the path variable means it should be depending on the path, but here we have generated something in spite of the fact the temperatures are different for each of the steps, the amount of heat which is absorbed is different, but the summation of that factor Q by T at that particular temperature plus the Q by T at another temperature are equal. And if they are equal, that means this will be equal to 0. So this minus this will be equal to 0. So this will be a minus sign. Okay. So this is what we have generated. We have generated a new state variable which is supposed to be Q by T. So now let us look at the statement which we have. Statement which we are going with the statement right now, and before discussing a few parameters. But what is the, based on Carnot's engine, based on Carnot's heat engine, it was Kelvin who suggested a statement for this. What this is actually what Carnot put forward, and it was obviously validated by Kelvin. What Carnot put forward is, if you have a machine which is working in cycles and you absorb Q amount of heat from the hot reservoir and convert the entire system into work, is not possible. That is what his observation was. So it is the negative form in which that statement is given. It is impossible for a system to operate in cycle that takes heat from a hot temperature reservoir and converts it to the work in the surrounding without at the same time transferring some amount of heat to the cold reservoir. So this is the statement of the Carnot. Actually, it is Carnot statement, and obviously postulated and formulated and validated again by Kelvin. So what is it which is saying that you cannot have a system which is operating in cycle, takes heat from the hot reservoir and continuously converts that into work into the surrounding without in the same time transferring some amount of heat to the cold reservoir. So this is the impossible system. For it to be possible, what you have to have, we have to have a amount of QL rejected to a low temperature reservoir. Okay. All the way I have written minus plus sign. Okay. Similarly, there is another postulate by Clausius. It's again an inverse sort of a um, statement. It is based on, say, a refrigerator. It is impossible for a system to operate in cycle that takes heat from a cold reservoir, that you take some amount of heat, that is Q is positive, you absorb some amount of heat, that the system is absorbing some amount of heat and transferring it to the hot reservoir and dissipating it to the hot reservoir without some amount of work being done on the system, or until you have a work done on the system, we cannot have a cold amount of heat from a cold reservoir being transferred to a hot temperature reservoir without at the same time converting some work into heat. Okay, so you have to apply some work to convert this, take this Q heat from a cold reservoir and transfer it to a hot reservoir. Okay, this is what we are doing in a, when we are doing a refrigerator, we are taking some amount of heat from, say, the room. In the room, we are taking out some amount of heat and we are putting that Q amount of heat to the outside. When you see the AC is on, the environment outside is going to be very hot. So you are increasing the temperature of the outside. But that cannot be done until you have a compressor system working on it. So we have to do a work on it. Only then you have this diagram possible. This diagram without a W input is not possible. So this is the statement of Clausius, which is again a negative statement. It's impossible to have a system to operate in cycle that takes heat from a cold reservoir and continuously supplies to the hot reservoir without some amount of work being input or some work into heat is converted. So this is one form of the second law definition, but there is a much more important version or mathematical representation of the Clausius law, and that is all spontaneous processes are reversible, and for the continuous process, a reversible process, what you have, the Q dq reversible, that means the heat which is absorbed or rejected over a cycle in a reversible cycle divided by temperature should be equal to 0. Okay. So here I am yet to define what is entropy, but we will define this as entropy. So in later discussion, which we are going to see that there is a term which is never written, that is dq irreversible. If the step is executed in an irreversible manner, even if one step in the cycle is irreversible, then the entire cycle becomes irreversible. So if you have a irreversible step in the process and that irreversible transfer of heat at that particular temperature will be less than equal to 0. Okay, but what another statement of okay, I have not yet defined what is q by t, so let us not look at it. So whenever we are writing the Clausius inequality, this is less than equal to 0, this is equal to 0. When we write out the Clausius inequality, then we have to remember that Clausius inequality for a cyclic process says that dq by t over a cycle is less than equal to 0. It becomes 0 equal to 0 when it is reversible, and it is less than 0 when it becomes irreversible. So whenever we are talking about dq by t without having a subscript of reversible and irreversible, you have to understand that dq by t is actually a combination of dq reversible by t plus dq irreversible by t. So if I look at this, dq reversible by t is always going to be 0 and dq irreversible by t is going to be less than 0. So why dq reversible by t over a cycle should be less than equal to 0 is understood. So whenever I put this as reversible q, then it becomes equal to 0. When I have irreversible, then I have less than equal to 0. So the Clausius statement of integral of dq by t actually includes the dq reversible term and the irreversible term. But when we are writing in general dq and not mention dq reversible, that means it is having dq reversible part as well as dq irreversible part. We'll be talking about this in great detail in a while from now. So before we move into the actual definition of what dq by t is, let us look at the various efficiencies of heat pump and refrigerator and a heat engine. Heat pump and refrigerator are almost identical. They are the same. What is the and heat engine is obviously slightly different. What is the purpose of having a refrigerator? Refrigerator purpose is to, what is the purpose? What is the output? You have a QC amount of heat which is the output, right? We are actually trying to cool a place. A refrigerator is, we are trying to cool a place. So some amount of DQC or the DQL is what the output is. The cold heat transfer on the at lower temperature is what is the output, and what we do as input, we have to do work for it. Okay, so the input is work and the output is the amount of cold heat which we exchange between the system and the surrounding, and this is the efficiency of a refrigerator. While you see for a heat engine, it is always the work which we want. Work is the output, and whatever input is the high temperature reservoir in contact with high temperature reservoir. Whatever amount of heat is exchanged from the reservoir to the system is the input, and what we get is the work done by the machine or the engine is the output. But when we are talking about a refrigerator, what we are trying to look at, we are trying to take away a amount of heat of lower temperature at lower temperature and trying to cool a place, and in the process we have to do some work. So our work is our input. So work is our input, well, while we are getting some amount of heat at the lower temperature as the output. What is the difference between heat pump and the refrigerator? Heat pump is like a heater. What we are trying to do? We are trying to heat up to giving an amount of higher temperature so that the input here is again work, but the output is different. Output is what you are trying to do is you are trying to heat up a environment, and that time if you want to heat up the environment, then the temperature which is supposed to be taken out from the system is not of lower temperature, it should be of given to a higher temperature system. So the heat pump and heat engine, the efficiencies are always not called as efficiency. They are called as efficiency. Is instead of efficiency we write to say it is coefficient of performance. And heat pump is a machine or a device that moves heat from one location, the source, at a lower temperature to another location, that's the sink, at a higher temperature. So we are taking some amount of heat from the lower temperature to a location which is higher temperature. So what we are taking out? We are taking out a lower temperature amount of heat to the from and to another location which is or at a higher temperature. So this is actually the function of a heat pump and heat or a refrigerator. When we are having a heat pump as a say heater, when heat pump being working as a heater, may be thought of a heater in its objective to warm the hot the heat sink, or a refrigerator if the objective is to cool the heat sink. So these are the two difference, but both the for both of them the input is work, the outputs are different. Output is one in one place you are trying to heat up the objective, and the other one is to cool up the objective. So based on that you can have this table of how to find out the efficiency. Heat pump and heat in refrigerator, the diagram is going to be the same. The diagram is going to be the same. Only heat engine is slightly different. You see the arrow of the work is going to be different, and so is going to be the direction of the QH transferred or QL transferred is going to be different for the heat pump and the heat refrigerator. Their diagram is going to be looking exactly identical. Any question here? Okay. Now I'm going to skip this. I don't know what is happening here. I'm going to skip this, but this is the postulations of Carnot's theorem. The efficiency of the Carnot theorem says that it is going to be always less than 1. There is no machine operating in the same temperatures of source and sink cannot have a efficiency more than that of the efficiency of the Carnot's engine, and that is always less than 1. And all reversible cycles operating between two temperatures having the same efficiency, that is what is the Carnot's efficiency, which is according to the Carnot's engine. These are the three consequences of the Carnot's theorem. Efficiency of the Carnot engine cannot be more than 1. No cycles having efficiency greater than Carnot engine is possible. Any two machines operating in the same temperatures will have the same efficiency equal to that of the Carnot's cycle. Okay. So, and this is to prove that no engine can be more efficient than a Carnot engine. I am going to skip that and move to a different topic. Now I've still not defined entropy. I've still kept my discussion to Q by T. So let us consider a system where this is the cycle which I have operated, and instead of all steps being reversible, I say let one of the steps be irreversible. This expansion, isothermal expansion, I say is carried out irreversibly. Rest of all of the steps are reversible. You have the adiabatic expansion reversible, isothermal compression reversible, adiabatic compression reversible. All the three steps are reversible, but only one step, the isothermal compression or expansion, is made irreversible. Now what happens? I have said already, whenever there is one step irreversible, the entire system turns out to be a irreversible engine. Okay, or entire cycle becomes irreversible. So now if you remember your work diagram, in the expansion and the compression diagrams, if you look at this was the expansion and this was the compression. If you remember, It was this was irreversible, this was irreversible, this was reversible compression, this was reversible expansion. Okay, and what we see here, if I look at the expansion, expansion means the system is doing work. And the system is if the system is doing work, that means work is negative. What you see in the expansion, the reversible work is going to be much more than the irreversible, right? So suppose I have this step 1 to 2 as a heat absorbed irreversibly in the isothermal expansion. What happens? Just have a look at what happens. I know that the W minus means what?
Work is done on the system.
On the system. And if I have a reversible and irreversible system, what can you say from here?
Ma'am, please repeat.
See, I have given this as a reference because I'm writing down this. Reversible work is greater than the irreversible work, right?
Yes, ma'am.
That we have taken, we have done before. But here I have written the expansion. This is the expansion isothermal. First step is the expansion step, isothermal expansion. Right? So
Yes, ma'am.
isothermal expansion, first step is made irreversible, and this is the isothermal expansion. And if I say what will be my internal energy change when I go from 1 to 2 through irreversibly, and what will be the internal energy change when I go from say 1 to 2 reversibly? Since it's a state function, they should be equal.
Yeah, zero. No change.
Okay.
Yes, ma'am.
So since it is whether I carry out the change reversibly or irreversibly, the value of delta H, delta U change from this place to this place should be same, because it is going to be W U2 minus U1 independent of whether it is irreversible or reversible.
Yes.
So if I take a reversible Q, the change in reversible U and irreversible U, the value of the U will be same. It will be U2 minus U1 independent of whether I am performing it reversibly or irreversibly.
Yes, ma'am.
Right? Right. So the Q will be changed from whether I for irreversible step and as well as reversible step, the value of delta U, that means U2 minus U1 from this step to this step will be the same. And what is U1? U1 is Q plus W. So you replace the Q plus W with one is irreversible Q and the other is the irreversible work. And here I have reversible Q and irreversible work. I'm just substituting the Q for each side. Right?
Yes, ma'am.
So now you have a look at what you see. The minus W, the minus W for a reversible step is greater than the minus W of irreversible step. That is why I've drawn this diagram to remind you. This is the first column is the irreversible, and this part is the reversible, and this is the number of steps in between. Okay, this is the diagram we had seen. This is the reversible step, and this is the irreversible step, right?
Yes,
So
ma'am.
reversible one, if I compare these two, expansion, these two, what do I get? The reversible work is greater than the irreversible work, right? Now plug in that here. Since u is not changing, since u is not changing for the two processes, whether it's irreversible or reversible, then I plug in the values of u in each step. One is irreversible and other is reversible, right? Now I say that the minus w is greater in the reversible step than the irreversible step. Then what should happen if one is greater?
The other one must be less.
With the minus sign is greater. Then what does it mean from this for isothermal expansion? For an irreversible isothermal expansion requires less heat than the reversible one. Yes?
Yes.
Yes, ma'am.
So the heat required in a irreversible expansion requires is less than the heat required in the irreversible step. So if I want to calculate the efficiency of this engine now, what will I have to write now? What will be the efficiency? Efficiency is nothing but 1 minus the QH by QL, right? Right?
Yes, ma'am.
Now, the efficiency now instead of QL and QH, I can now subscript that with reversible and irreversible part, because here QH is irreversibly put in. I was not trying to show this because I have written a plus sign all throughout. This will be a minus, right? Please compute it yourself, otherwise it will be very confusing. Epsilon is 1 minus QC by QH, or QL by QH. That is the efficiency of Carnot engine. Now I write down, I say that if the step which is irreversible, one step is irreversible, then the machine becomes irreversible, or the device becomes irreversible. So when one step is irreversible, I denote that efficiency of that device as efficiency irreversible. Where all the steps are reversible, I denote that, subscript that efficiency as Q reversible. Right? Minus sign in both the sides. So you now see what is, if I further write, what will be the steps in the irreversible? The Q, which is input, is irreversible, and Q, which is rejected to the lower temperature sink, is reversible. This is irreversible and this is reversible. That is why the machine becomes irreversible, and I say that is the efficiency of a irreversible device. Right?
Yes, ma'am.
Now compare these two. Compare these two. This is a minus sign. This is a minus sign. This is a minus sign. This is minus sign. And that is why I was not trying to show this, because it's going to be getting confused. You are going to get confused if you are not writing a minus here. Here it is a minus. Here it is a minus. Here it is a minus. Now tell me, from here I have said that Q reversible is greater than Q irreversible. For an isothermal change, for an isothermal expansion, the irreversible isothermal expansion requires requires less heat than the reversible one? This is just now we proved, right? So here what you, if you plug in here, which is the reversible one? This is the reversible one and this is the irreversible one. And which is greater? This is greater, right? Are you with me?
Yes, ma'am.
This is greater, and if this is greater, this will, the entire fraction will be smaller.
Yes, ma'am.
And since this is going to be smaller than this one, the comparatively this fraction will be slightly higher.
Yes, ma'am.
So 1 minus the higher fraction will be obviously having the value of epsilon calculated will be lower than this value of epsilon calculated when I am having this. Clear?
Yes, ma'am.
So if you put this minus sign, then the confusion will go. Please put this minus sign. Please put this minus sign. I will correct it. So from this, I can make out that the efficiency of a reversible heat engine will be always greater than the irreversible one. And how can an irreversible engine be generated? For any one single step becoming irreversible, the entire device becomes irreversible. And this is coming from the fact that the process which we have just now taken is the heat which is in an irreversible isothermal expansion requires less heat than the heat which is required for a irreversible one, a reversible one. And that comes from the fact that delta U for the change for the isothermal expansion from 1 to 2 is going to be same whether it is carried out reversibly or irreversibly. If minus W is greater, then the plus W will be smaller, and then that is why Q will be higher to make it equal. Q reversible will be higher. Am I clear? So
Yes, ma'am.
the Carnot in any engine will become equivalent to a efficiency of a Carnot engine, provided all steps are reversible. If even one step becomes irreversible, then the entire cycle becomes irreversible, and the efficiency of that engine will be lower than that of the Carnot's engine. Am I clear?
Yes, ma'am.
Okay. So what we have yet not introduced is the term entropy. Now let me introduce the term entropy. Clausius inequality was something which we have already discussed, and from if you can look at this, if you say Q reversible is going to be greater than Q irreversible, so if I take a temperature at which the process is being the Q is being transferred, you just have a look at it, that Q reversible by T will be greater than Q irreversible by T, right? Q reversible is greater than Q irreversible. The heat absorbed in the isothermal step, expansion step, is going to be much more if it is done reversibly than that of the system which is carried out irreversibly, right? That is why we said
Excuse me,
that
ma'am. I have my NSO class from 6.
Okay. So I will just do this last. I'm not going to start entropy right now. I'm just saying then the ratio of Q reversible by T will be greater than irreversible by T, right? Agree?
Yes, ma'am.
Yes,
So
ma'am.
if that is so, then if this is equal to 0 for a Carnot cycle, that means this has to be less than 0. Understood? And this is the Clausius inequality. I said Q integral Q by T is less than equal to 0. If it becomes equal to 0, that means it's a reversible cycle. I know that for a reversible Carnot engine, Q by T is equal to 0. But if this is equal to 0 for an irreversible step, if I say, then if it is 0 is greater than that, that means it has to be negative. Am I clear?
Yes, ma'am.
So Q irreversible by T, if I have for a system over a cycle or for a number of steps, will be equal to less than 0. But we never write Q irreversible by T ever. It is only to make you understand that if I have Q reversible by T, this I will define as entropy. This will be equal to 0 for a cycle, but this will be less than 0 because this is for a cycle is equal to 0, and this will be 0 will be greater than this. That means this is going to be less than 0. And that is the Clausius inequality we have. Greater than equal to 0 for a complete cycle. If it is reversible, it is less than 0. If it is irreversible, it's less than 0. If it's reversible, it's equal to 0. Okay. Then tomorrow we meet again.